Hi friends, in this session of non-parametric test we study about the chi-square. So first I would like to define about the chi-square. The chi-square test is one of the simplest and most widely used non-parametric tests in statistical work. The chi-square test was first used by the Carl Pearson in the year 1960. The quantitative chi-square describes the magnitude of the discrepancy between the theory and observation. It is defined as chi-square is equal to summation of O minus E whole square over E, where O refers to the observed frequencies and E refers to the expected frequencies. Here one more thing, degree of freedom. While comparing the calculated value of chi-square with the table value, we have to determine the degrees of freedom, which is equal to V is equal to N minus K. V is for degrees of freedom, where N is total number of observations and K refers to the number of independent constants. In contingency table, the degree of freedom V is equal to C minus 1 into R minus 1, where C is number of columns and R is number of rows. I will explain to you later about the contingency table in the example. So now we see the application of chi-square test. So here look at in this box. The few important application of chi-square tests are given here. The test of independence, test of goodness of fit, Yates correction for continuity, test of population variance, and test of homogeneity. So first of all, we will study about the test of independence, which is also called the contingency table analysis. So look at here, the chi-square test of independence is used to analyze the frequency of two qualitative variables or attributes with multiple categories to determine whether the two variables are independent. The chi-square test of independence can be used to analyze any level of measurement, but it is particularly useful in analyzing nominal data. So, contingency table, when observations are classified according to two qualitative variables or attributes and arranged in a table, is called a contingency table. Nominal data I have explained earlier in my previous session. In spite of that, here you can take one look of nominal data. Okay. Now, for example, whether voters can be classified by gender is independent of the political affiliation. These sort of questions we could simplify through this contingency table analysis. Whether university students classified by gender are independent of courses of study. Whether wage earners classified by education level are independent of income. Whether type of soft drink preferred by consumer is independent of consumer's age. Whether absenteeism is independent of jobs classification. Whether an item manufactured is acceptable or not is independent of the shifts in which it was manufactured. So for this all we have to study. We will take one tutor example for better understanding of this chi-square test. Now we see one tutor example for better understanding of this chi-square test. In an anti-malaria campaign in a certain area, quinine was administered to 812 persons out of a total population of 3,248. The number of fever cases is shown below. So look at here, the contingency table is already given to us for observed frequency. There are two things, one is fever and second one is two variables we have. One is fever and another one is quinine. Quinine is the treatment. So look at here in this table, the persons who are suffering with fever and given quinine is 20. The persons who are not suffering with fever and given quinine is 792. The total persons who has given quinine is 812. Similarly, the persons who are suffering with fever and given no quinine is 220. The persons who are not suffering with fever and given no quinine is 2216. So in this way, the persons who has not given quinine is 2436. Now the persons who are suffering with fever is 240 and the persons who are not suffering with fever 3008. The total number of population we have taken here 3248. So we give some name to this. First I would like to give the name the persons who are having fever. I will put here A1, and the persons who are not having fever, the persons who are given quinine, I write down here B1, and the persons who are not given quinine is B2. Now it is the intersection of A1 B1. So we could write here B1. B1 is this one, B2 is these two, and similarly we could write here A1 and A2. So this is our we could say that A1 B1, intersection of A1 B1. This is A2 B1. It is A1 B2. It is A2 B2. This is the contingency table of observed frequency, and this one is N we have, the population size. Now what we take the assumption here in our hypothesis, the null hypothesis would be no relationship or association exists between two variables, fever and quinine, that is they are independent. It will mention they are independent, and in respect the alternative hypothesis would be a relationship exists, that is the fever and quinine are related. So first of all we have to find out the expected frequency for this, because we don't know the frequency distribution of this data. We don't have any expected frequency distribution, so we will get it through the contingency table we will make for the expected frequency. How we get these expectations of AB? So look at here, AI Bj is equal to AI into Bj over N. So N is here. So how we get it, I will explain you here. First of all, if you have to find out the A1 B1, the first look at here, it is A1 B1. We have to find out the expected frequency for A1 B1. So we get here A1 B1. A1 B1 is equal to, so this is our, I write it down here, it is B1, it is B2, it is over A1, it is over A2 and N. What we have to do, we have to write down the totals, whatever the totals in this expected frequency contingency table. We will write it down the totals only. We will keep blank the internal columns of this where we have to put the expected frequency. So how we get the expected frequency, I explain it here. So it is A1 B1, A1 into B1. So A1 we have 240 and B1 we have 812, and we would divide it by N. So N is 3248. So we get here 60. Now we get A1 B2. A1 B2. So A1 is 240 we have, and B2 is 2436 divided by 3248. So we get here 180. Now A2 B1, we get here A2 B1. So A2 B1 would be 812 into 3008 divided by 3248. So we get here it is 752. And finally we get A2 B2, which is 3008 into 2436 over 3248. It is, we have 2256. So this we have got here Now if we have to check, we could add these all, or it should be equal to 3248. If we add these all, we get the same. So the summation of this is 3248. So now we put down these values here in appropriate places. So here we will put down 60, A1, B1, and A1, B2 we get here 180. Here we are putting down 752, and here 2256. Okay, so this we have got the expected frequency with the help of contingency table. Now we put down this value here in analytical table we have made here. So what we have to put down, first observed frequency we have to put down 20, 220, 792 and 2216. So I put down here 20, 220, 792, 792, and the last one is 2216. 2216. The same we have to keep it from the expected frequency table of contingency. 60, 180. Here we write down 60, 180, 752 and 2256. 2256. Now we get out the difference of this O minus E. So 20 minus 60 is minus 40. 220 minus 180 is 40 plus 40 we have. And 792 minus 752, it is plus 40 again. And 2216 minus 2256, it is minus 40 again. Now we get the square of these all. So we get here the square of minus 40 is 1600. The square of all is 1600 here. 1600. Now we divide this O minus E whole square by expected frequency, what we have got here, the 60. So we divide it by 60, 1600 divided by 60. We simplify here in this column, we have to write O minus E whole square divided by E. So O minus E whole square is equal to 1600 divided by E 60 here. So we get here 26.667. 26.667. Now in the second we get here 1600 divided by expected frequency is 180. So we get here 8.889. 8.889. Here 1600 divided by 752, we get here 2.128. And finally 1600 divided by 2256, so we get here 0.709. Now we get the total of these, the summation of these, we get here 38.393. So we have got here 38.393. Now we see the table value in the chi-square table. So look at here, it is the chi-square table, 5% we are checking it out. So look at here at the 5%, the degree of freedom, first of all we have to find out. So I explain you how we get the degree of freedom, this sort of contingency table. So here you see we are in a contingency table, the degree of freedom V is equal to C minus 1 into R minus 1, where C is the number of column and R is the number of rows. So look at here, in contingency tables we have 2 columns and 2 rows. So the degree of freedom would be degree of freedom V is equal to C minus 1 into R minus 1. So column are 2 and rows is also 2. Sorry, 2 minus 1. So we get here 1 into 1. So degree of freedom is 1. So we have to look at this degree of freedom 1. So here at 5% the value is 3.841. So chi-square table value at alpha critical point at alpha is equal to 0.05, the critical value of this 3.841, so which is equal to 3.841, and we have the chi-square calculated value, what we are getting here, 38.393. So it is 38.393. It means the calculated value is greater than the table value, so it is rejected now. If we are beyond this, so it's rejection. If we are under this, our value, calculated value is under this value 3.841, so it is accepted. Our null hypothesis is accepted. It is less than, but it is more than this. The 38.393 is more than 3.841. It is very much more than. So it is rejected. So here we could say that our hypothesis, the calculated value of chi-square, the calculated value of chi-square is greater than the table value. The hypothesis is rejected. It means hence quinine is useful in checking malaria. So in this way we could get on the conclusion of any assumption or the hypothesis through chi-square.